Hello, hi, good morning, good afternoon, good evening. This is Tasien. I'm happy to be here again. Welcome to Mathify Analytics. I hope you are going to enjoy today's presentation. But guess what? What are we going to talk about today? In today's video, we are going to talk about discrete probability distributions. Whether you are a beginner in these concepts or if you are an expert, I hope you're going to gain some insights from this video. So make sure to watch this video from start to the end if you want to know how to construct a discrete probability distribution and its graph, and you want to know how to determine if a distribution is a probability distribution. We want to know how to find the mean, the variance, and the standard deviation of a discrete probability distribution. And you also want to know how to find the expected value of discrete probability distribution. And hey, we will work on all discrete probability distributions. I mean the Bellinoulli distribution, the binomial distribution, the geometric distribution, and the Poisson distribution. So you see, this video is very important. I hope you're going to watch it from start to the end. So let's start. Let's recall first what is a random variable. A random variable represents a numeric value associated with each outcome of a probability distribution. It is mostly denoted by x, and one example is the number of sales calls a salesperson makes in one day. Yes, if you are a sales person and you have to make calls, and if I describe a variable, then I call it number of sales is that you make in one day, sales calls that you make in one day. So this can be a random variable. And another example, time spent on sales calls in one day. So you see, these are two different things. These are two different things because in the first one, let me take my pointer so that we can use it. Yes, in this first example, you see that this number of sales calls, you can count them. You know, I made 1 2 3 4 5 6 7. I made, let's say, 7 calls. But when you are asked to count the time spent on sales, this is you cannot say 1 2 3 4. You may say, let's say, 20 minutes, this is an interval. 20 minutes, you can say 30 minutes, and this is an interval. You can say 2 hours, and that's an interval, but you can't say 1 time, 2 times. So yes, this is not countable. So these are both random variables, but two different types of random variables. One is discrete and the other one is continuous. Yes, so in today's video, we are going to focus most on discrete random variables. And what is a discrete random variable? First, a discrete random variable has a finite or countable number of possible outcomes that can be listed. Like in these previous examples, the number of sales calls, these you can count them. You may say, I made 3 calls. I made 10 calls. Yes, so then a variable like that, which has finite or countable numbers of possible outcomes that can be listed. So this is a discrete random variable. And you can see that here you can count number of calls. I made 0 calls, I made 1 call, I made 2 calls, I made 3 calls, 4 calls, or 5 calls. So this is a discrete random variable. I hope you understand what is a discrete random variable now. If you have understood it, write in the comments, yes, I have understood. Now I know what is a discrete random variable. But if you have not understood, write, I don't understand very well. Then we will come and comment on your comment and explain more. But I hope this is understandable. So let's move on and take an example. we are going to go in these examples, and then you are going to decide if my example is a discrete random variable or if it is not a discrete random variable. The number of stocks in the Dow Jones Industry Average that have share price increases on a given day. The number of stocks in Dow Jones Industrial Average that have share price increases in a given day. Is this a discrete random variable or it is not a discrete random variable? Can we count the number of these stocks, or we cannot count them and list them out? If we can count them and list them out, we can, let's say they are 5 or they are 10, they are 100 stocks. So then it will be a discrete random variable. But if not, it is not a discrete random variable. Write in the comment, is it discrete or not? So this is a discrete random variable because the number of stocks whose shares price increases can be counted. You can count them like 0 stocks, 1 stock, 2 stocks, 3 stocks, 10, 30 stocks, 100 stocks, 1,000 stocks. So you can count them. So this is a discrete random variable. Okay. Now, every discrete probability distribution has to list each possible value the random variable can assume together with its probability. And secondly, it must satisfy the following conditions. And the first condition is that the probability of each value of the discrete random variable is between 0 and 1 inclusive. And in symbol, mathematical symbols like this, we say that the probability distribution, the probability value of each random variable of each value will be between 0 and 1, and 0 included and 1 included. This is one condition that has to be satisfied to be a probability distribution. And the second one is that the sum of all the probabilities should be equal to 1, or the probabilities has to sum to 1. So these are the two things that everyone needs to know about probabilities. Probability distribution. First of all, is that the probability of each value of the discrete random variable, not even the discrete random variable, even for continuous random variable, but in this video I won't talk about discrete random variable. So then each value of the discrete random variable is between 0 and 1. The probability should be always between 0 and 1. The maximum probability is 1 and the minimum probability is 1. And if you are calculating probabilities, then you find that you get 2. So that is not the probability. If you get minus, let's say minus 0 point something, that's not a probability. It is a positive value which is between 0 and 1. And secondly, when you sum up all the probabilities of a random variable, the sum should be equal to 1. So you get it? Get it. So if you get it, that in the comment section that you have got it. Like, got it? Yes. So let's try to see how we can construct a discrete probability distribution. If you want to construct a discrete probability distribution, let's say you have x, which you want to be a discrete random variable, and it has these possible outcomes. It has n outcomes, x1, x2, up to x1, xn. So to make the probability distribution of this random variable, first you have to make a frequency distribution for the possible outcomes. This is the first thing that you have to know. You need to know the frequency distribution, and then secondly, you need to find the sum of the frequencies. Yes, and then third, you need to find the probability of each possible outcomes. How do you find the probability of each possible outcomes? You have to divide the frequency that you have calculated in 1 by this total sum that you have calculated in 2. So let's see. And finally, you have to check if all the probabilities you find are between 0 and 1, and also you have to sum up all the probabilities and see if they sum up to 1. Let's see one example. Let's see one example here. We have an industrial psychologist administered a personality inventory test for passive aggressive traits to 150 employees. And individuals were given a score from 1 to 5, where 1 was extremely passive and 5 was extremely aggressive. And a score of 3 indicated neither trait, neither passive or neither passive or aggressive. Then construct a probability distribution for the random variable x. Then graph the distribution using a histogram. I have listed here like I had a sample of I have listed here of how many people among the 150 employees, how many people had this score 1, how many people had the score to be 2, how many people has the score to be 3, and how many people had the score to be 4, and how many people have the score to be 5. So our variable here, it has 5 possible outcomes from extremely passive to extremely aggressive. So it can take only 5 possible outcomes, either 1 or 2 or 3 or 4 or 5. So among the 150 employees who were ranked, 24 of them had the score 1. 33 of them had the score 2. 44 had the score 3, and 30 has the score 4, and 21 had the score 5. This is the frequency distribution. And then next we have to calculate the probabilities. How do we calculate the probabilities for each value? We take the frequency. Let me go back here. We have said that find the probability of each possible outcome by dividing its frequency by the sum of the frequencies. So in our question here, the sum of frequencies is 150. And the frequency for score 1 is equal to 24. So the probability will be equal to 24 divided by 150. And the probability of x equal to 2 will be equal to 33 divided by 150. And so that's what I've listed here. I've said that the probability x equal to 1 is 24 over 150, which is equal to 0.16. Probability that x is equal to 2 then will be 33 over 150, and so on. And the probability that x is equal to 5 will be equal to 21 over 150, which is equal to 0.01. So what you have to check next, you have to check if all these probabilities you get, they are between 0 and 1. Is it correct or not? Yes, it is correct. All the probabilities are between 0 and 1. This is between 0 and 1, between 0 and 1. All the probabilities are between 0 and 1. And then next, what you have to do, you have to sum up. You have to sum them up. If you sum up, you see that the sum is equal to 1. Since the sum is equal to 1 and all the probabilities are between 0 and 1, so the probability distribution of x is this one, and this is a random variable, and it is discrete because we have the score to be either 1, 2, 3, 4 or 5. So all right, I hope from this example you now understand how to construct a discrete probability distribution. First, the frequencies and the sum of all the frequencies, and then the probability for each value of the variable, so which is obtained by taking the frequencies divided by the total frequencies. And then you have to check if every probability content is between 0 and 1, and if the sum is equal to 1. So next we is to construct the histogram of this probability distribution. What do? We have scores to be on the x-axis and the probabilities on the y-axis, and then you place the values of x. The values of x in our case, they are 1, 2, 3, 4, and 5, and these are the probabilities. So we have seen that the probability that x is equal to 1 was 0.16, so it's somewhere here, and the probability that x equal to 2 was 0.22. Was it 0.22? Yes. And the other one was 0.28, so you see it here, 0.28 somewhere here, and the other one was 0.20, so you see here 0.20, and the other one was 0.14, so 0.14 somewhere here, and this is the histogram. So it's that each bar here in the histogram has the area to be equal to 1 times the probability times by its probability, because this is 1, and this length also from here to here also we have 1, and from here to here also we have 1, and from here to here we have 1. Yes, then the height here is the probability. So each bar, area of each bar is equal to the probability of each value here, because we have one times its probability, and here also 1 times this probability, and here also this length is 1, then 1 times its probability. So each bar here has the area which is equal to the probability of the corresponding value of x. So you see, that's it. Now we know how to construct a discrete probability distribution. Know the frequencies, and then check if the frequencies are between 0 and 1. Let's see if they sum to 1, and we can also make a histogram like this. Isn't it good? Yes. If you like the video, click like. So let's move on. Yes, but now what do we call expected value? You know, the mean, the variance, and standard deviation. But what do we call the expected value of a random variable, or of a discrete random variable? Because here we are talking about discrete random variables. The expected value of a discrete random variable is equal to the mean of the random variable. So the way you have computed the mean is the same way that we compute the expected value of a random variable. Here I have one interesting example of how we can compute expected value, and I hope you are going to enjoy it too. I enjoyed it when I was preparing it. Finding an expected value. Let's take this example. At a raffle, 1,500 tickets are sold at $2 each for 4 prizes of $500, $250, $150, and $75. So we have 1,500 tickets, and each ticket is sold at €2. And the prizes, we have 4 prizes: 500, 250, 150, and 750. So the question is, if you buy one ticket, what is the expected value of your game? If you are participating in this raffle, and you know that each ticket is sold at 2 euros, and you have to buy one ticket. So what are you expecting to gain? What is the expected value of your gain? The expected value of your gain. So let's calculate it. First, your gain for the price 500 will be 500 minus 2, because you have bought a ticket of 2 euros. 2 euros, $2. And if you get a price of 250, your gain will be 250 minus 2, which is equal to $248. And if you happen to get the price of $150, your gain will be 148. I am subtracting this, the $2 that you have used to buy the ticket. And if you get the price of 75, then your gain will be 73 euros. But what if you don't get the price? Your gain will be minus $2. So your gain is a loss. Your gain is a loss. But we are not yet done. But what is the expected? Because we have for 500 tickets, you don't know if you are going to win or if you are not going to win. So what should be your expected value to gain? So let's see. First of all, let's construct the probability distribution. The probability distribution will look like this. Why? Because for the gain of 498, we only have one person among one winning ticket among the 150 tickets. And for this prize also, we have one winning ticket. Then one out of these 1,500. We also have one winning ticket, which will win this 148, and one winning ticket which will win 73 euros. And the other ones, the remaining ones, because we had the 1,500, only four of the tickets can get these winning values, and the remaining one, so it's 1,500 minus 4, which is 496. So those we get a gain, a negative gain, a loss. We get a loss. So this is the probability distribution. All right, so having this probability distribution, now we are good to go and calculate the expected value. As I have told you, the expected value is equal to the mean. So here we need to calculate the mean of this probability distribution. And as we have done before, the mean is the sum of the product of the values times their corresponding probability. So we take this 498, we multiply by its probability 1/500. This times this times this times this, and this times this, and we sum them together. And when we calculate this and sum them together, the sum will be minus $1.35 US. So do you expect it to gain? Your gain is negative. Please, when you are participating in that, don't expect it to gain. Your expected value is a loss. Here, at least in this level, your expected value is a loss. Don't expect it to gain. Expect to lose 1.35 US. You can expect it to lose an average of 1.35 for each ticket you buy. If you buy one ticket, expect it to lose this money. If you buy two, then expect to use 2 times this one. So you see, all right. So this is the expected value, and I hope now you understand what is expected value and what is the mean. The mean and the expected value is the same. All right. If we summarize, we have defined a discrete random variable. We have constructed a discrete probability distribution in the graph, and we have determined if a distribution is the probability distribution, and we have also found the mean, the variance, the standard deviation of a discrete probability distribution, and we have finally found also the expected value of a discrete probability distribution. Did you enjoy this video so far? If you have enjoyed, click like and share the video to your friends. But we are not yet done. We still have many things to learn about these discrete probability distributions, because there are different types of this kind of discrete random discrete distributions, and I need you to keep watching the video if you are still interested to know these different types of discrete random variables. So let's move on. So then what is next? Next we are going to see the Bellinoulli and binomial distributions, and let's start with the Bellinoulli distribution. And the Bellinoulli distribution will be a discrete random variable which takes two values, 1 or 0, and 1 with probability p, and 0 with probability 1 minus p. And this x equal to 1 is interpreted as a success. We consider it to be a success. Here are some examples. X equal 1 for heads in coin tossing. When we toss a coin, we have two possible outcomes, either a head or a tail. So if we consider a head as a success, then x equal to 1 for heads, and then x will be equal to 0 for tail. And another example is the x equal to 1 for male in a survey. So if we are in a survey and we are labeling whether a person is a male or a female, we can choose to label a male as a success, then 1, and 1 as and 0 as a female. Sorry for females. But then if we choose to label males as x equal to 1, then female will be labeled as x equal to 0. And another example is when we label x equal to 1 for a defective in a test of a product. If we are testing if a product is defective or not, we can label it as x equal to 1 when we found it defective, and if it's not defective, then x will be equal to 0. And another example here is the x equal to 1 for made the sale, for when we are tracking performance. Yeah, if I'm tracking whether I have made the sale, if I am a sales person, of course, if I'm tracking whether I have made a sale or not, then I can choose to label making a sale as 1, then not making a sale as 0. Yes. So then how do we compute the mean and the variance for a Bellinoulli distribution? Let's start with the expected value, and the expected value is equal to the mean. We have seen it earlier. So this is the sum of all possible values times their corresponding probabilities, and we have seen that we have either 0 or 1. So for 0, x equal to 0, the probability is 1 minus p, and for x equal to 1, the probability is p. And when we sum up these, we get p. So the expected value or the mean of a Bellinoulli distribution is equal to the probability of success. And the variance, if you remember the formula, we have to take x minus the mean. The mean here, because our mean expected value that we have found here is p, then we have to subscribe to what is it? Substitution. To substitute. Yes, p as the expected value p, then x minus p squared times the probability of each x. And if x is equal to 0, then we take 0 minus p squared times the probability that x is equal to 0 is 1 minus p, as we have seen it here. when x is equal to 0, the probability is 1 minus p, and when x is equal to 1, the probability is p. So that's why multiplying by 1 minus p here when x is equal to 0, and we have to multiply by p when x is equal to 1, and when we sum up this we get p. So the expected value is equal to p, and then for the variance we will take x minus p, then squared times the probability, and then we substitute x by its value, and we have 0 minus p. This p here, I mean this one, is this one, the expected value, if you remember the formula. So then we will, if we sum up all this together, we will get the variance to be equal to this product, the product of probability of success times the probability of failure, if you like. And some people will choose to write them, also write it down, because some people will choose to write. Do I have a pen? I'm not sure, but some people will choose to write the probability of failure, this 1 minus p, to be equal to q. So some people will use q, and if they use it q, then our product there will be, this product will be equal to p minus this q. So if you choose to use the probability of failure to be equal to q, then the variance will be equal to the probability p times the probability q. Yes, so that's it. So I know, do we need some examples in practice of this Bellinoulli distribution? I think we can skip this and then go to the Bellinoulli, the binomial distribution. The binomial distribution. So what are binomial experiments? Binomial experiments. First of all, the experiment is treated for a fixed number of trials, where each trial is independent of other trials. In binomial experiments, we have one experiment which is repeated. We have to repeat it many times, but a fixed number of times, and each trial will be independent of other trials. No one depends to the other trial. Independence. And then the next one is that there are only two possible outcomes of interest for each trial. The outcomes can be classified as success or as failure. But the experiment is repeated many times, and you have to mark whether you have a success or a failure for each trial. And the trials are independent. No one depends to the other one. And next, the probability of success is the same for each trial. Having a success, we have the same probability of having a success. So, again, the random variable x counts the number of successful trials. We have an experiment. We repeat the experiment many times, and for each repetition we have to mark whether we have a success or a failure. Then the random variable that takes the number of successes among those trials that we have tried will be known as a binomial experiment. I hope you have understood this. Let's try to describe these mathematical symbols that we use. N, we denote n the number of times a trial is repeated. So the number of times our experiment is repeated, we denote it as n. And we denote p the probability of success in a single trial. And that probability is the same for all the trials. And we denote q the probability of failure in a single trial, and that probability is equal to 1 minus p. And x is the random variable that represents a count of number of successes in any trials. If, for example, we have made 5 trials, we have to uh, mark whether we have 0 successes, or among the 5 we have 1 success, or among the 5 trials we have 2 successes, 3 successes, 4 successes, or 5 successes. So that random variable will be called a binomial experiment, or a binomial random variables. The experiment is repeated n times, and trials are independent. No one depends to the other one, and each trial has the probability of success for each trial is the same for all trials, and the probability of failure is, of course, is equal to 1 minus the probability of success. So if we count how many successes we have among the n trials that we have performed, that random variable that counts those possible successes, it will be a binomial experiment, or a binomial distribution. Let's see some examples. Decide whether the experiment is a binomial experiment. If it is, specify the value of n, and the value of p, and the value of q, and list the possible values of the random variable x. First example. We are at the hospital now. And a certain surgical procedure has an 85% chance of success. Those who had at least one surgery, when you go for a surgery, you are like, am I going to be alive? Am I going to get out here alive, or I am going to die? So for a surgical procedure, there is 85%, but this is an assumption. I'm not saying that that's true. So, but suppose that there is 85% chance of success, of having a successful surgery. So then it means that 50% we will have a failing surgery. A doctor performs the procedure on 80 patients. We have a doctor, and he has performed the same procedure for on 8 different patients. You see, we have a surgical procedure, and he has repeated 80 times, because we have 8 different persons who are going to go to have the same surgery. An experiment which is repeated 80 times. But you see that there is independence. If we are operating Tassien, and the next person is going to be operated, let's say we are operating James. So the operation which is done to James will not depend on what has happened to Tassien. No. There is no dependency. There is no dependency between the procedures. You see, we have independence. We have a procedure which is repeated many times. Then the random variable represents the number of successful surgeries, and we are counting how many among these 8 people has passed the surgery successfully, or how many of them did not made it to succeed, and then they died. Okay, so is this a binomial distribution? If it is, what is n, what is p, what is q? This is a binomial experiment. This is a binomial experiment, but why? Because first, each surgery represents a trial, and there are 8 surgeries, and each one is independent of the others, as I have been saying. And secondly, there are only 2 possible outcomes of interest for each surgery. It may be either a success or a failure. I may get out from the surgery room alive or I may pass away. So either success or a failure. And then the probability of success, PS, is 80% for each surgery. And then the random variable X counts the number of successful surgeries. So you see, N is 80, P is 0.85, and then Q will be 1 minus 0.85, which is 0.15. So you see, this is a binomial experiment. Yeah, that's it. And the number of successful surgeries, they may be 0. If we have 0, it means that all the 8 people who had the operation died. If we have 1 success, it means among the 8 people who had the operation, all the 7 died, only 1 is alive. And if we have 2 success, it means that 2 of the 8 ones had a successful one, they are alive. Then the 6 ones did not made it, they passed away. And if we have X equal to 3, then 3 made it. And if you have 4, then 4 made it. All 5, all 6, all 7, all the 8 people may survive the surgery and no one died. Yes. Okay. So now you see, this is a binomial experiment. Let's see another example. We have a jar that contains 5 red marbles and 9 blue marbles and 6 green marbles. And you randomly select 3 marbles from a jar without replacement. We have a jar and it has marbles with different colors, red and blue and greens. And we have to randomly select 1 without replacement. When we take 1 out, we don't take it back. And the random variable represents the number of red marbles selected. So is this a binomial experiment or not? Is it a binomial experiment or not? So this is not a binomial experiment, but why? This is not a binomial experiment because first, the probability of selecting a red marble on the first trial will be 5/20 because there is altogether there are 20 marbles. So, and 5 of them are red. So the probability of selecting a red one will be 5/20. But because the marble is not replaced, the probability of success, it means the probability of selecting red for subsequent trials is no longer 5/20. Because, for instance, for the second trial, it will be 4/20 because 1 is taken away. And for the other one, it will not again be 4. It will be 3. So you see, we don't have the same probability of success. So since we don't have the same probability of success, already we don't have a binomial experiment. Because for the binomial experiment, the probability of success should be always the same for all the trials. And the trials are not independent because the probability of success is not the same for each trial. Because for instance, for the second trial, the probability depends on whether we have selected we have succeeded for the first trial or not. If for the first trial we have succeeded and we took a red one, so then the probability for the second trial will not be the same. But if we have failed for the first one, then the probability will be still the same. So you see, the probability depends on what we have selected at the preceding selection. So this is not a binomial experiment. Yes. Then for the binomial probability, we have this formula. The probability of success in any trial is given by this one. It's px having x success will be equal to the combination of x in n times the probability of success power x times the probability of failing power n minus x, and when you expand it, you have it this way, where n is the number of trials, and p is the probability of success, and q is the probability of failure, and n is the number of success in any trials. Yes, so let's see here a practical example of how we can compute the binomial probabilities. Suppose that in my microfraction surgery, a microfracture knee surgery has a 70% chance of success on patients with degenerative knees. The surgery is performed on 3 patients. N is equal to 3, and the probability of success is 0.75. So then find the probability of surgery being successful on exactly 2 patients. We need first to make the our probability distribution, and there is 2 methods, and one method is to use this tree diagram, because we are asked to find the probability of surgery being successful on exactly 2 patients. So, and we have three patients. So for the first patient, first surgery, we may have a success or a failure. And for the second surgery, when we have had a success, surgery for the first one will be either a success or a failure. And here again, success or a failure, and again and again. So for this first one, we may have all the three people had a successful surgery. So we will have outcomes S. This means that the 3 people had a successful surgery. And here we have two people have a successful surgery. And how many possible events? We may have the first and the second having a successful surgery, or we may have the first and the third, or we may have the second and the third having a successful surgery. So we have 3 possible of having two successful surgeries. And we have also 3 possible cases of having one person having a successful surgery. Either the first person has a successful surgery, and the second and the third have failed, they died. Or the first died, the second survived, and the third one died. And you may have the first and the second died, and the third one had a successful surgery. And we have only one possible outcome of having no successful surgery. Then the 3 people died. Oh God. Yes. So in this case, to compute the probability of having 2 successful surgeries, and we are going to use the multiplication rule, we have to know where we have 2. Where we have 2 is here and here and here. And the probability of having this will be what? It's at this stage here. To have the first surgery successful, we have seen that there is the probability of having a successful surgery is 75%. This is 3/4. Yes, so that's why I have here 3/4, and here we will have then 1 minus 3/4, which is 1/4, of course. And again, here we will have the probability of success is 3/4 and 1/4, 3/4 and 1/4, 3/4 and 1/4, 3/4 and 1/4, 3 over 4 and 1 over 4, 3 over 4 and 1 over 4. So that's why to have this combination, we have 3 over 4 times 3 over 4 times 3 over 4, because to have a first successful surgery is 3 over 4 and 3 over 4 for the second person and 3 over 4 for the first person. And the same, we can compute these probabilities this way, and I think you can see it. It's just multiplying the probabilities that we have here. For instance, for this case, we have the probability as this 3 over 4 and here 3 over 4, but here is 1 over 4. That's why we take 3 over 4, we multiply by 3 over 4, and we multiply by 1 over 4, and so on. So, having two successful surgeries, we have to add together this plus this and plus this. Yes, this plus this plus this. So we take this and plus this and plus this. So when we add them together, we get 0.422. I have here 9 over 64, because I have 9 over 64, 9 over 64, and 9 over 64, and I'm multiplying by 3. Or you can take 9 over 4 or 64 plus 9 over 64 and plus 9 over 64. Yeah, so I don't want to confuse you. It's normally the addition. Here we have multiplication, but here we have to add them together. This plus this and plus this. Yes, if we use the multiplication rule, it has to be done this way. But what if we use the binomial probability formula that we have seen earlier? This formula. We can also use this formula, and then we have to compute first. We have n equal to 3, and the probability of success, this is 75%, and then the probability of failure is 1 over 4, and x is equal to what? Equal to 2, and then we replace everything by its value. N by its value, that's 3, p by its value, x by its value, this is 2, and p by its value 3 over 4, and q by its value 1 over 4, and we compute it, and we will get the same value, 0.422. So which method is easier for you? I think using a formula is easier. Yes, using a formula is easier, because here we have used this probability tree, because we only have two persons. But what if we have many persons? If we have more than 2 persons, then it will be difficult for us to compute, to write that diagram tree. It will be easier for us to use this formula. So I recommend you to use this formula than using the tree. But if you want to understand it better, use a tree. All right. Yes. Okay. Then the binomial probability distribution will list the possible values of x with the corresponding probability of each. When we are constructing a binomial probability distribution, first list all possible value of x with the corresponding probability of each, and next then we can write the probability distribution, and this is the example that we have been doing up here. This microfraction, this example here, this one. So for the if we use this example to have 0 failure, then no one has succeeded. So if we go to this diagram 3, is this probability is 1 over 64, because we only have one case, 1 over 64, which is equal to that 0.016, and the probability, and then we may have only one person has a successful surgery, and this probability will be equal to this, And when we have 2, the probability is equal to this, as we have computed it up here in this one. And when we have 3, x equal to 3, the probability is equal to 0.422. Yes. So it is recommended to use the binomial formula to get all these probabilities. Yeah, it's easier that way instead of using the diagram tree. Yes, all right. Okay, so now let us learn how to construct a binomial distribution. And let's use this example to construct a binomial distribution. In a survey, workers in the US were asked to name their expected sources of retirement income. 7 workers who participated in the survey are randomly selected and asked whether they expected to rely on Social Security for retirement income. Then create a binomial probability distribution for the number of workers who respond yes. So we are in a survey, and they asked people if they will rely on Social Security retirement or not. So our task is to construct a binomial probability of a distribution for the number of workers who responded yes. So 25, it is said that 25% of workers, Americans, experts relies on Social Security for retirement income. So this is the probability of success for our random variable. The probability of relying on American Social Security retirement is 25%, and 7 people were it is said that 7 workers who participated. So number n for our case is 7. So because 7 people were asked, and the probability of relying on Social Security for retirement is 0.25. Then Q will be 1 minus 0.25 to get 0.75. So we already have our n is equal to 7. The probability of success is 0.25, and the probability of failure, it means not relying on Social Security, will be 0.75. So among the 7 who were asked, we may have 0, no one of them will rely on Social Security, or one of them will rely on Social Security, or 2 or 3 or 4 or 7, depending on whether they said yes or no. Okay, so then next, what do? We have to calculate the probability of having x equal to 0, or of having x equal to 1, or having x equal to 2, or and so on, or x equal to 7. How do we do it? I have recommended you to use the formula that we have seen. So using the formula, the probability that x equal to 0 will be given by this one. So n is 7, x is equal to 0, p is 0.5, and q is equal to 0.75. So 0 and 7 minus 0 will be equal to 7. And when we compute it, we get this value. For x equal to 1, then 7, n equal to 7, and x equal to 1. So here we have power 1. Then here we have 6, because in the formula it says n minus x, and x here is 1. Then 7 minus 1 will be equal to 6. And when we compute it, you get this one, and so on. We replace each value by its corresponding value. X by its value, n by its value, p by its value, and q by its value. Then we get these probabilities, and the final probability distribution will be this one. For x equal to 0, the probability is this one, and for x equal to 1, we have this probability. For x equal to 2, we have this probability. For x equal to 3, we have this probability, and so on. For x equal to 7, we have this probability. So to have a probability distribution, this should sum to 1. When we make a sum, we will have 1.0001. So you see that this is approximately equal to 1, of course, because we have used the decimal numbers. We are not having exactly one, but it's closer to one, and it's correct. So then, like this, we have our probability distribution constructed. This is a binomial distribution already constructed. And let's see another example here. A survey indicates that 41% of women in the US consider reading their favorite leisure time activity. What is your leisure time activity? Do you also like reading? Oh, yeah. I'm not fan of reading anyway, but those who are fans of reading, women, US women, 41% of them, they like reading in their leisure activities. You randomly select 4 US women. So we have our n to be equal to 4 because we randomly select 4 US women and ask them if reading is their favorite leisure time activity. Find the probability that at least 2 of them respond yes. So in our case, n will be equal to 4 and p will be equal to 41%. Yes, so n is equal to 4, p equals 0.41, and q, then it's 1 minus 0.41, which is 0.59. So the probability that at least 2, if we say at least 2, it may be 2 or 3 or 4. So we have to compute the probability that 2 of them they read, or 3 or 4. Then we add them together. The probability that we are asking is probability p x equal to 2 plus x, p x equal to 3 plus x equal to 4. So we have to find these 3, then we add them together. Okay, we are going to use the formula again. So if we use the formula for x equal to 2, just replace x by its value here, 2, and then we complete the probability. You get this one. For x equal to 3, replace x by its value here, 3, and 3, then 4 minus 3 is equal to 1 here. And when we replace 4, we have 4 here and 4 here, then 4 minus 4 here, we have 0. And we have these probabilities. And the probability that we have been asked of having at least 2 among the 4 reading, having reading as their favorite hobby in their leisure time. So it will be the probability that x is greater than or equal to 2. Then p2 plus p3 plus p4. Then we add them together to get this one. See, it is easy. I hope from now you understand well what is a binomial distribution and how to construct that binomial distribution, the probability distribution, and how to calculate the probability, any probability that you can be asked about the binomial distribution. But one bonus, I have a bonus for you, and this bonus is here. Now we are doing something a little bit different, and this is a bonus. The results of a recent survey indicate that when grilling 59% of households in the United States use a gas grill. If you randomly select 100 households, what is the probability that exactly 65 households use a gas grill? So now we have 59% of households use the gas grill, and we move to into make a survey. We take 100 households and we ask them if they use a gas grill when they are grilling. So then what's the probability of having among those 600 households visited, what's the probability that 65 of them, exactly 65 of them, use a gas grill? And then I said that's the bonus because we are going to do this using technology tool to find this probability. If we use a formula, it is easy. We have already seen how to use the formula, but then how about using a technology tool? Which technology do you choose? Some like using Python, others use R, others use Excel, others use Minitab or whatever. So I have a bonus for you. I have one bonus one bonus for when we are using R. When we are using R, or what we need to know, we have N. Our N is 100, and K or whatever X. I wrote K here, but you can use X because we are using X. So X will be 65, and P, the probability of success, is 0.59. And what you do in R, you just write D binom. The D binom will give the probability, and you enter K and N and P, then you run, then you will get this value. Then you will get this value immediately. Yeah, I mean this value. So this is R. The probability of having exactly 65 households using a gas grid is 0.0394. And another bonus, using Python. In Python, what do? In Python, we also have to at least import one library. From this library, SciPy stats. This is a library which is used much in calculating different statistics. So we have to import the binomial distribution because we need to use the binomial distribution, and then we just write binom.pmf. PMF. This is the probability mass function. PMF. So binom.pmf, probability mass function. Then you enter your parameters K, N, and P, and then you run it. So you will also get the same value, 0.0391 when you run it. And another bonus, the last bonus, is using Excel. In Excel, you just this is a function, that's why you have equal, then equal the binom distribution. Then you enter your parameters, 65, this is K or X, then N, and the probability. Then false of course, because we need exactly. Then exactly X equal to 65. So we get the same value. This 0.039107. So you see that all these displays, either this one in Python, or the other one in R, or this one in Excel, all of them, they give the value to be 0.04 when we approximate it. So you see, this is the bonus, and I hope you like it. Is it? Yes. Yes, so that's that probability of having 65, exactly 65 households using the gas grid, which is 0.04. Yes, is this bonus good? So those who are interested in technology, you can either use that Python or R or this Excel, whatever you want. So we don't need to just deal with this calculation by hands. You can use whatever tool you need. But hey, I have another bonus. Guess which one? I have another bonus. I want now to use the table, probability distribution table. We are going to find the binomial distribution, binomial probabilities using a table, and we are going to do it for on this example. About 30% of working adults spend less than 15 minutes each way commuting to their jobs. When they go to work, they spend 15 minutes each way. 50 and how many? 30%. So the probability of spending 15 minutes each way when they are going to work is 30%, 0.3. So you randomly select 60 working adults, and what is the probability that exactly 3 of them spend less than 15 minutes each way commuting to work? Then we are going to use a table to find this probability. So using a table, what do? We need to know N, and for our case, N is 6 because they have selected 6 working people, and the probability of using 15 units when they are going to work is 0.3, because we have 30%, and X number of people, X, we are asked to find among the 6 people how, to find the probability of having 3 of them using at least 50, using less than 15 minutes to go to work. So on the table, what do? You need to know n. We have n and x and p. So these are the probabilities, and these are n and these are x's. So n, in our case, n is equal to 6. We have 6 here, and x is equal to 3. So you go to 6 and you find 3. This is 3, okay? And the probability of success is 0.3. So 0.3, and you go all the way, and here 3 and 0.3. So the probability is 0.185. So you see, I've given bonuses. Bonus using technology and bonus using a table. And you also know how to calculate it using a formula, or how to calculate the probabilities using 3 diagrams. So isn't it good? So you have learned a lot. This is a lot. So now we are going to see how to graph a binomial distribution. Graphing a binomial distribution. And we are going to use this example. And 59% of households in the US subscribe to cable TV. You randomly select 60 households and ask each if they subscribe to the cable TV. Construct the probability distribution for the random variable x. Then graph the distribution. How many people were selected randomly? 6. So we have select 6 households here. Yes. So our n is equal to 6. So then x will have values from 0 to 6. And 39%. And the probability of success is 39%. So yeah, we have this. We have n equal to 6, p equals 0.59, and q then is 0.59. 1 minus 0.59, which is 0.41. And then the probability for each value of x, and x will take how many values? 0, 1, 2, 3, 4, 5, and 6. So we are here. When we use the formula, you can use the formula. Then when we use the formula, the probability of having x equal to 0 will be equal to C1. You can use whatever, either a formula or a technology tool or a table, whatever you use. Then this is the probability distribution, and the task was to compute, to graph this. How do we graph these ones? We have 0, 1, 2, 3, 4, and 6. And I've told you earlier, when we have been talking about the general case of discrete distributions, we have equal size the balls. So, and the size, and here we have 1. The length should be equal to 1, 1, 1. The length of each bar should be equal to 1, and then the height should be the probability. And for x equal to 0, the probability is 0.005. That's why we have some values here. This histogram. And the probability for x equal to 1 is 0.04, somewhere here. And so on. The probability for x equal to 2 is 0.148. So approximately 0.15. And so on. And I've told you that the area of each bar should be equal to the probability of that, the corresponding x. So the probability that x equals to 0.005, the area should be equal to 0.005, and so on. So that was it. That's how you can just make a histogram. I don't know if you will be making it by hands or by using a technology or whatever. I hope in the future, maybe in the coming videos, I will make exclusive video about using these tools, R or Python. We'll be using R or Python to just calculating these probabilities and making the graph. Then you will see how to make these graphs. These are histograms, and of course the cumulative graphs too. We will also do them. Okay. Now next, how do we compute the variance, the mean, the variance, and the standard deviation for the binomial distribution? The mean is equal to n times p. I think you will be able to derive this formula using the fact that it should be the summation of x times the probability of each axis. So if you try to derive it, then let me give it as a homework. Write in the comment, at least in the comment section, write in the comment how we can derive this formula or this one. I think it's very easy. You will be able to derive it, but the mean is equal to n times p, and the variance is n times p times q, and then the standard deviation will be the square root of the variance. That's it for the binomial distribution. Maybe we can take one example and see how we can compute the mean and the variance and the standard deviation. Let's see this example. In this city, I don't want to read the names, they're being difficult to read. Pittsburgh in Pennsylvania, about 56% of the days in a year are crowded. Find the mean, the variance, and the standard deviation for the number of crowded days during the month of June. Interpret the results and determine any unusual values. So, in this city, about 56% of days in a year they are crowded. So we are asked to find the mean and the variance and standard deviation for the number of crowded days during the month of June. So then we have to interpret the results and determine unusual values. So first we need to know n. In June, how many days do we have? In June we have 30 days. That's why we take n equal to 30. And the probability of having a crowded day is 56%. Then the probability of having a non-crowded day is 0.44. So the mean will be equal to n times p, as the formula says up here, n times p. So the mean will be equal to 30 times 0.56, which is equal to 60.8. And the standard deviation by formula is n times p times q. N times p times q. So 30 times 0.56 times 0.44, which is equal to approximately 7.4. This is the variance. And then the standard deviation will be equal to the square root of 2.7. So we have already found the mean, the variance, and standard deviation. But we are also asked to interpret the results and determine any unusual values. So all what we have is that the mean is, it's like in June we are likely to have approximately 17 crowded days. Approximately we will have approximately sorry for the disturbing. Yes, we will have approximately 17 crowded days. But the standard deviation is 2.7. What does it mean? What does it mean? And how do we find the unusual values? All what we have to know is that on average there are 16.8 crowd days during the month of June, but the standard deviation is about is about 2.7 days, and then the values that are more than 2 standard deviations from the mean are considered unusual. So what does it mean? It means when we take this mean 16.8 and we subtract 2 times the standard deviation, and the standard deviation is 2.7, so we get 11.4. So this means that in June, having a June with 11 cloudy days would be not usual. It is unusual. But again, when we add 2 standard deviation to the mean. Here we have been subtracting. So, and then here when we add again 2 standard deviation to the mean, we will have also unusual cases. So this will give us 22. Also a June of 22 cloudy days will be also unusual. I don't know if it's correct in US. So those who are watching from US, is it correct? Is it normal to have 16 cloudy days in June? But is it also usual to have less than 11 cloudy days? So how many approximately? Those who live in US, type in the comment and let us know how is the weather there in June. Yes. Yes. In summary, or what have you seen now? Up to now we have determined if a probability experiment is a binomial experiment, and we have found the binomial probabilities using the binomial probability formula. We have also found the binomial probabilities using technology and a binomial table. We have graphed the binomial distribution, and we have found the mean, the variance, and the standard deviation of a binomial distribution. And that is for the binomial distribution. But is it all that we have to say? We have more discrete probability distributions, and we still have two more discrete probability distributions, and in these ones we will learn about geometric distributions and Poisson distributions. And let's start with the geometric distribution. A geometric distribution is a discrete probability distribution first, and it satisfies the following conditions. First, a trial is repeated until a success occurs. We repeat an experiment, and when we get a success, we stop. An experiment is repeated until a success occurs. It's not like in binomial distribution. We repeat experiment, and when we reach a given number, we stop there. But for geometric distribution, we have to repeat until we get a successful event. Yes. And next, it also satisfies this condition. The repeated trials are independent of each other. We also have independence like for binomial distributions. And next, the probability of success P is constant for each trial. We also have the same probability of success. So the difference between binomial and geometric is that for the binomial, we don't need to have a success to stop. Yes. But for the geometric, we stop only when we have a success. Yes. So, and the probability that the first success will occur on the trial X is equal to P times Q times X minus 1, where Q is equal to 1 minus P. Yes. So let's see some examples. From experience, you know that the probability that you will make a sale on any given telephone call is 0.23. Find the probability that you first sail on any given day. Find the probability that your first sail on any given day will occur on your fourth or fifth sailor's course. So how do we deal with this? The probability that our sailors of four on fourth or fifth course will be equal to the probability of having x equal to 4 or of having x equal to 5. And then geometric with probability p equal to 0.23 because it has been said that making a series on core, the probability of making a series on a core is 0.2023. So then q will be 1 minus 0.23, which is equal to this one, and x is 4 and 5. And we apply this formula, this formula q times p times q power x minus 1. So then for x equal to 4, we will have p is 0.23 times q 0.70, then x is 4, then minus 1. Then for x equal to 5, we will have 5 here, 5 minus 1. So we have these two probabilities, then we sum them together, we add them together. So the probability of having a sail on the fourth or the fifth core then will be equal to 0.186. Yeah, that's it. So then the next probability distribution that I want you to know is the Poisson distribution. What is the Poisson distribution? It is also a discrete probability distribution, and it satisfies the following conditions. First, the experiment consists of counting the number of times an event x occurs in a given interval. So now we have a given interval and we have to count number of success that we had in that given interval. The interval can be an interval of time or an area or a volume. So then the probability of the event occurring is the same for each interval. For each interval, the probability of having that event will be the same. And again, the number of occurrences in one interval is independent of the number of occurrences in the other intervals. But before going on the example, let's see how we express the probability of having an event, a Poisson event. The probability of having an event x will be equal to mu power x times e times power minus mu over x factorial. And what is mu and what is e? E is this famous Euler number, and the Euler number, which is approximately equal to 2 times 7 2.71818, and mu is the mean number of occurrences in that interval or in that volume or in that area, depending on what event we are talking about. So let's see one example of a Poisson distribution. The mean number of accidents per month at a certain intersection is 3. Follow me well. We have the mean number of accidents per month. Which interval? We have an interval of time, which is a month. And there may be accidents in a given corner. I don't know, given intersection, there is mostly to have an accident, but the mean number of having accidents at that intersection of roads is 3. Then what is the probability that in any given month 4 accidents will occur at this intersection? So you see, we have an interval. An interval that we are taking here is a month, and the event that we are tracking is having accident, knowing that the mean value of having an accident in a month is 3 accidents. So if we are in June then they ask you how approximately what is the probability, no, what is the probability of having 4 accidents in this June month. How then are you going to compute it? So we will use this formula, or what we have to know is the value that we are calculating. We have x equal to 4 because we are finding the probability of having 4 accidents in a given month, and knowing that the mean of having mean accidents in a month is equal to 3. So we apply the formula. This is mu power x times u Euler e power minus mu, and minus the mean over x factorial, then over 4 factorial, then we get that one. Yeah. Yes. Yeah. So you see, all what you have is that to know is that for the Poisson distribution, we are tracking events in a given interval of either interval of time or interval of area or interval of volume. So we have an interval, not just a single point, just an interval. Then we track a given event and see if that event occur or not, knowing that we have a mean value of that event to occur in a given interval equal to that one that we are dealing with. So yes, so that's it. And of course, that's it. I hope you have enjoyed this presentation, and you might have many questions. If you have questions, don't hesitate to write in the comment section, or you have our email. Send the email to me and ask any questions you need to ask. I hope this video will help you to understand the basics of probability, because probability distributions are very important, and you can't understand the continuous probability distributions if you have not understood the discrete probability distributions. I hope you are going to revise these and ask questions, of course, to understand them better. Yes, remember to share the video and subscribe if you have not subscribed, and I hope to see you next time. Bye.